In this topic, we will learn about the building a virtual prototype facility from vision to reality. Today, we'll explore how to build a state-of-the-art virtual prototype facility that transforms the product development process. This cutting-edge lab leverages immersive digital environments to bridge the gap between imagination and engineering excellence. By creating virtual prototypes, teams can rapidly iterate, test, and refine designs before physical manufacturing. Holographic displays, AI-powered simulations, and collaborative workspaces empower engineers to bring their ideas to life in a digital realm. This facility represents the future of product development, where innovation and efficiency converge to deliver groundbreaking products. The key objectives of establishing a virtual prototype lab are to reduce physical prototyping costs by 40 to 60% and accelerate design cycles from months to weeks, securing buy-in from key stakeholders across engineering. Design and management is critical. Build a compelling business case to secure funding and executive sponsorship. Thoroughly research available virtual prototyping platforms, hardware options, and integration capabilities that align with your organization's technical ecosystem. Develop a strategic rollout plan that balances quick wins with long-term vision. Start with pilot projects to demonstrate value before full-scale deployment. Premium VR headsets like the MetaQuest Pro offer untethered freedom with high resolution, while the Varjo XR3 delivers unparalleled visual fidelity for detailed CAD work. Tethered systems provide superior graphics, processing power, and reduced latency, which is essential for complex simulations requiring real-time rendering. When selecting hardware, it's important to balance factors like comfort, resolution, field of view, and tracking accuracy against budget constraints. SAD integration with platforms like SolidWorks and Autodesk enables seamless model import with parametric capabilities. Intact VR development tools like Unity and Unreal Engine offer robust prototyping environments with physics, simulation, and interactive scripting. Ensure software compatibility with existing engineering workflows and scalability for future technological advances. Virtual prototyping and testing allows engineers to import CAD models directly into VR environments. This enables full-scale, immersive design reviews that reveal spatial relationships impossible to assess on 2D screens. The iterative design process is accelerated. With real-time feedback loops between designers and engineers, immediate modifications can be visualized instantly, speeding up the design cycle. Physics-based simulations can be incorporated to validate performance. Testing things like stress points, aerodynamics, and mechanical functionality. This allows for thorough testing in the virtual space before physical production. Collaborative VR sessions enable remote or on-site teams to interact with prototypes simultaneously. Regardless of location, this facilitates seamless teamwork and feedback across distributed engineering groups. The key focus of this slide is on how IoT systems can enable real-time data management and synchronization across digital and physical environments. It highlights four main areas: IoT integration, cloud infrastructure, live, synchronization, plus and security and compliance. For IoT integration, the goal is to connect virtual prototypes with live sensor data to create a dynamic feedback loop between digital and physical testing. The cloud infrastructure point emphasizes the importance of centralized data storage, version control, and collaborative access across distributed teams. Live synchronization refers to the bidirectional data flow that maintains consistency between digital twins and real-world iterations. Finally, the security and compliance aspect ensures robust data protection protocols and adherence to industry standards like ISO 27001. The overall message is about leveraging IoT capabilities to enable seamless, secure, and synchronized data management across the digital-physical continuum. Virtual prototype facilities allow engineering teams to experience, test, and refine their designs in immersive digital environments. This blurs the boundaries between imagination and reality, enabling teams to iterate on their ideas before committing to physical production. The advanced technology in these facilities allows for highly realistic, interactive virtual experiences that closely mimic the physical world. This empowers engineers to make more informed decisions and catch potential issues early on in the design process. Ultimately, these virtual prototyping capabilities help drive innovation and accelerate the path from concept to final product. Virtual environments must be designed with user comfort and safety in mind. Prioritize ergonomics to minimize motion sickness and visual fatigue during extended VR sessions. Implement clear protocols for the physical VR space to prevent collisions and accidents. Establish guidelines for session durations that balance productivity and user well-being. Comprehensive onboarding is crucial to ensure staff can effectively use VR tools and understand platform capabilities. Scenario-based training simulations. Allow for hazardous operations practice without physical risk exposure. Continuous learning programs are important as VR technology and workflows continue to evolve. This slide provides an overview of the key steps in developing a simple virtual prototype environment. We'll start by importing a 3D CAD model of a mechanical component into a VR platform like Unity, ensuring the materials and geometry translate accurately. Next, we'll add interactivity to the model, allowing users to manipulate, rotate, and inspect it from any angle. We'll also implement annotation tools for marking design considerations. Then we'll incorporate basic physics simulation to test movement, stress distribution, or mechanical behavior under various conditions, validating functionality before physical prototyping. Finally, we'll configure multi-user access for collaborative design review sessions, enabling geographically dispersed teams to examine and discuss the prototype simultaneously in a shared virtual space. The Fisker Karma is a luxury electric vehicle with a sleek, distinctive design. Fisker Automotive faced the challenge of validating the complex rear structure's crash safety performance. They needed to minimize costly physical testing iterations and accelerate the certification timeline. The engineering team deployed comprehensive virtual prototyping to simulate crash scenarios and analyze structural integrity. This allowed them to optimize the design before committing to physical prototype construction. Virtual testing eliminated multiple physical prototype cycles and reduced rework expenses by around 35%. It also accelerated the safety certification process by several months. This demonstrates the tangible ROI from investing in virtual prototyping for complex product design. The key takeaway is that early virtual validation prevents expensive downstream corrections while maintaining rigorous safety standards. Effective cross-disciplinary collaboration is key to success in virtual prototype facilities. Establish regular coordination meetings and shared objectives to prevent siloed workflows and ensure integration between software developers, hardware specialists, and engineering teams. Managing the complexity of large CAD assemblies with thousands of components is a major challenge. Implement robust version control, optimization strategies, and clear naming conventions to maintain seamless physical-virtual integration. Balancing visual fidelity and performance is critical. Ultra-high visual fidelity can overwhelm hardware and cause lag. Destroying user immersion. Strategically optimize geometry and texture resolution to maintain engagement without compromising essential design details. The future of virtual prototype facilities is an exciting and rapidly evolving field, with several key trends to watch. One of the most significant developments is the use of AI-driven design optimization. Machine learning algorithms can now suggest design improvements within VR environments, automatically optimizing for factors like weight, strength, manufacturability, and cost. Another important trend is the expansion of digital twins. Virtual prototypes are increasingly linked to live operational data from deployed products, enabling continuous refinement based on real-world performance and usage patterns. Finally, cloud-based VR technology is democratizing access to sophisticated virtual prototyping capabilities. Streaming VR will enable global real-time collaboration without requiring expensive local hardware, making these tools available to a wider range of organizations. The virtual prototyping approach has a transformative impact on product development, reducing costs by 40 to 60%, compressing timelines from months to weeks, and improving design quality through early validation. Building a dedicated virtual prototyping facility requires careful planning, selecting the right technology, and designing user-focused workflows that integrate seamlessly with existing engineering processes. Start with focused pilot projects that demonstrate clear value, then iterate based on lessons learned. Scale your virtual prototyping capabilities progressively to maintain a competitive advantage. The future of innovation is immersive, connected, and collaborative. Embrace this future today and transform how your organization innovates.